Hello, this is the second lecture on simple circuits and resistors. And in this lecture, we're going to look at circuit diagrams and the concept of parallel and series circuits, as well as Ohm's law. So you can see here on this first picture that we represent the different things we're going to be using in a circuit with symbols. And you'll see pictures that have these symbols on them to show the different things that we want to talk about. So for instance, a battery, which looks something like this, if it's a AA battery, is represented by this line, vertical line here, a vertical line there, and then these other parallel lines of different lengths. They actually represent how a battery is built, because the battery is actually often built with layers of different materials stacked upon one another, and that's what that symbol represents. And it could also be turned on its side. I should note too that battery isn't always vertically oriented, it could be horizontal. A wire, which is used to connect a battery to other things, is represented by typically just straight lines. A resistor, which we've been talking about, is represented by a straight line here and then zigzags in there, and then another straight line after. And we'll be using resistors in lab and talking about them. And then, of course, a light bulb is something else you'll see in circuit diagrams. We'll be using light-emitting diodes this semester rather than light bulbs because they consume a lot less energy, although they have some differences in how they work. But a light bulb is represented by a circle with a little squiggle in it to represent the filament. So that the diagram often has some physical meaning in relation to how the actual circuit element works. Now I'm going to talk about when we wire them. You're going to hear me use the words series and parallel quite a bit. Series means that the elements are wired end to end, like you can see in this case for these batteries. They're wired in series in this case. If you were to wire them in parallel, then there would be this wire here that's connecting the top of both of them, and this wire here that's connecting the bottom of both of them. Now they're wired in parallel. And even though it may make sense when you see me talking about it here, sometimes when you're wiring it on your circuit board, it can get confusing. And that's what lab is for. And we'll be doing that plenty in lab. But this is the two basic ways that you can start wiring things up and connecting them in circuits. We're also going to be measuring aspects of the circuit. If we want to measure current, we use something called an ammeter, and that's just this little circle here with an A in it, with a wire on each end. And typically what we do is we put an ammeter directly into the circuit where we want to measure the current, and I'll show you how to do that. You put it in series with the thing you want to measure, with the object or the circuit element whose current that's passing through it you want to measure, because you want the electrons to move through the ammeter. So it makes sense that you'd put it in series. A voltmeter, on the other hand, which is something else we'll be using, we'll use it to measure voltage. That's represented by a little circle with a V in it. That's its symbol. And when we measure voltages across objects, we're actually going to be putting the voltmeter in parallel with the object, which makes it actually easier to do than an ammeter in order to make measurements. And you'll see, and we'll talk about that a lot more. And if I was to draw a simple circuit that has a battery and a light bulb, I can show you how we would connect a voltmeter to it. A voltmeter would be, in this case it's not a battery and a light bulb, it's a battery and a resistor. The voltmeter would be placed in parallel with the resistor. If I were to measure current, the current would actually be placed in the wire right here. We'll do examples of that later. The next topic that we're going to discuss is also on the homework and on the first lab, and it's called Ohm's law. And what Ohm's law does is it relates for a certain type of devices, which resistors are an example of, devices called ohmic devices, which isn't very descriptive, but we'll talk more about that. It represents the relationship between the voltage, V, the current, I, and the resistance, R, in the circuit. And it's a simple formula. It just has three terms in it, kind of like F equals MA. It basically says that if you have a fixed resistance in a circuit, which you often do, you have a resistor of a certain size, and you pass a current through that resistor, a certain number of electrons passing the resistor every second, then you're going to get a certain voltage that you're going to measure across the resistor with, you could measure it with a multimeter. If you increase that current, you're going to increase that voltage. That's what this equation tells us. That's for a given resistor. If you keep the resistor fixed, that's what's going to happen. Similarly, if you, let's say you change the resistor, you put in a bigger resistor and you have the same sized current that's passing through, whether it's a big or a small resistor. If you increase the value of the resistor, you're going to increase the value of the voltage for a given amount of current that's passing through the resistor. So you have to keep the current fixed in order to understand this relationship in its basic form. In reality, you're going to be varying a lot of things in the circuit, or a few things. Both the current and the resistance may vary depending upon the circuit, but the voltage will be the product of the two of them. And this is what we're going to explore a little bit in the first homework and in the lab. You can also rewrite this equation as I is equal to V divided by R. So you divide both sides of this equation by R, and you get I equals V over R, which tells us the size of the current that's flowing through the circuit if you have a certain voltage put across a resistor. So you can change your battery, maybe go from a 1.5 volt battery to a 3 volt battery. Well, your current is going to double if you do that, based on this equation here, because your voltage doubled. So in this case, your current will double. And here's a practice problem. If you had a 12 volt battery and the resistance was 6 ohms, what current would be flowing in this circuit? And of course, the next question I could ask you also is, if you could measure the voltage across the resistance, in this case, if you were putting a voltmeter there, what would the voltmeter tell you? That's the other question I could ask you. There's your answers. The current would be 2 amps because it would be 12 volts divided by 6 ohms. And the reading on the voltmeter would simply be the reading of the battery in this case, because there's just a single battery and a single resistor, and we'll talk more about that. Why is that the case? The other thing about current, think about current kind of like water. Current flows through a channel, the channel being the wire. And if the wire branches off into 2 wires, well, some of the current's going to go one way and some of it's going to go the other way. Similarly, if you have 2 wires coming together, they can join at a junction, and another wire can emerge from that. And it's kind of like you're getting 2 streams coming together. And the current in the single junction, where after they merge, is going to be the size of this current plus that current. That's what the summation sign means. So current, electrical current, just like water current, is conserved. The amount of charge passing through, just like the amount of water passing through a space, has to be the same. What's coming in has to be equal to what's coming out. And that's known as Kirchhoff's junction law. But you can basically, if it comes up, it's the amount of current coming in has to equal the amount of current going out of a junction, where a junction is where several wires meet. And that'll help us think about circuits as we talk more about them. And here's an example of a place where you have 2 resistors that are wired in parallel in this case, with a a voltage supply here, or a battery, I should say, and there's going to be a current passing from the battery. But when it comes to this resistor, some of the current's going to go that way, and then some of it's going to continue on at that junction and go to the other resistor and then flow down there. The interesting thing is, how much current is it? And we'll talk about that shortly, but so you know that the current can branch off and break off. And most wiring in houses, this talks about a solar suitcase, which is something that I had students actually work with when we could work all together, which we can't right now. So you're not going to have a solar suitcase, which was fun. You can wire circuits up, but you're going to have your kit, and that's going to be fun too. And you can actually do more with that in some ways than what we could do with a solar suitcase. Make more measurements. We can do a lot more labs with it. But lights are basically resistors, and when you wire lights up, like in your house, or in this case in the solar suitcase, you actually wire lights in parallel. And you can kind of think about why that's the case. In your house, for instance, when you turn off a light here, there's a way you can turn it off, but the other one will stay on. That's the neat thing about parallel circuits. In series, if we were to wire lights in series, that wouldn't be the case. Again, we'll talk more about that. This is an introduction. But you can see that in this case, if all these resistors are in series and I pulled one of these resistors out, then I'm breaking the path that the current can take, and current won't flow through any of them. But if they're in parallel, like in this case here, if I pull this resistor out of the circuit, there'd be a big blank space here. The current would just all go to the other resistor. And what we're going to find is that this kind of makes sense. This relates current and resistance and voltage and resistance. That when I have resistors that are in series, there has to be the same amount of current flowing through each one, because there's nowhere else for the current to go except through the next resistor. Now when resistor, and it doesn't matter what the size of the resistor is. One is big, one is small, when they're in series. When they're in parallel, there could be different amounts of current flowing through each one. But the voltage, it turns out, is going to be the same when they're all wired in parallel. Now you might wonder, why is that the case? And here's what I use. I think of voltage as climbing a hill. So if I'm on the ground and I have to climb a hill, I have to go up a certain voltage. So this is the top of the hill on one side of these resistors, and the bottom of the hill is on the other. So if I climb the hill this way, I'll get to the top. If I climb the hill this way, I'll get to the top. If I climb the hill this way, I'll get to the top. Now, one route might be steeper than another. That's why we pick trails that go maybe a little less steeply than just climbing up the side of the hill. But in the end, the height I'm at is going to be the same distance above the ground as it was, no matter what path I took. You can think of the same thing electrically as that when you're thinking about parallel resistors. And that's all I'm going to speak about right now. That's the end of the lectures, really, for the first week, where we're talking about Ohm's law and resistance and series and parallel. That'll get you through the first homework and the first lab, and we'll continue with this in the next set of lectures.